The following video will be about technology and limitations and not fake conspiracies within the consumer and sometimes not consumer computer and electronics industries. We're going to talk about wavelengths, power consumption, and high-tech items, and my knowledge from 1990 is not really changing much because it didn't need to. Let's say 2002. It's a long time ago, 20 years ago. You had a processor that ran at 2 gigahertz, and it had a wavelength for that 2 gigahertz if it was a sine wave. It isn't. That was about 6 inches. Internally, the processor could be doing very different speeds. Lots of them, by the way. So in that 6-inch wavelength, you had a transition that would happen like this if it was smooth. What happened is it would turn it on and turn it off in that distance, because time is distance now. And this is through copper and silicon and aluminum. Most chips use aluminum, by the way. In fact, all of them I know of at the time and even today. And that would produce heat. And in a distance of 6 inches, if you went from 1 to 0 and back again, the same wire could effectively have a 1 and 0 at each end with a consequent current flow apparently trying to happen in it. So that's how electronics works. Okay. What about 2013? Well, it's 4 gigahertz, so it's a 3-inch wavelength doing it. Oh, that's getting close to the size of what we perceive as the chip. Let's talk about today's $600, 500 gigahertz CPU. $600 fucking dollars. The silicon square, the wafer as it's called, is 20 millimeters by 15 millimeters. It's in a package that's it's 45 millimeters by 37 millimeters approximately. And that's in a package that has a ball grid array under it. That's not really important, but what that means is that it either goes into a socket or it's permanently bonded to the board by heating up that grid array of ball solders to bond to the board. Due to the copper and aluminum having propagation delays in them, the size limitation here, we're now talking 5 gigahertz. We're working with heat dissipation and propagation delays in aluminum and copper and other materials, with it pumping out 100 watts of consumption, and a pretty good portion of that is just heat. And that's got a wavelength budget, I'm going to call it, of 2.37 inches or 6 centimeters. That's not really the limit, right? That means that one end of the chip to the other, depending on the internal actual frequencies, the same wire or the same acknowledged bit of data can have 2 different values from one end to the other. Now, in radio frequency equipment like on your cell phone tower or in a satellite orbiting the Earth, they accommodate for that because they do it in such a way that they can flow the data through. And they deliberately create delay line effects or extra gating, which causes delays, to do this so that it comes out exactly right. They just find out where the problems are and solve them. You might see old circuit boards where they have little curlicues of wires going in weird patterns if you flip them over. Those are delay lines to make sure that all the data that's supposed to arrive at the same time on the same set of wires has the same value when you change them all at the same time. And that actually is where the word glitch comes from. Bug comes from an actual bug being in a relay, by the way. So let's make a hypothetical 10 gigahertz processor, because Moore's law, we should double every X number of years, and we're long overdue. We're at 1-inch wavelength, 30 millimeters, approximately. These numbers don't match. I'm talking about what we call them in each country. That's supposed to happen in 2000 what? Now, you may have noticed that the computer industry has decided to switch over to putting lots of processors on one package. Lots of cores. Well, that improves performance. Okay. Transistors, as you scale them down in size by, let's say, you make them half as wide and half as tall. A transistor, capacitor, whatever component. Let's say it goes from this big to this big. That's not half the surface area of the screen, is it? That's a quarter. And if you do it three-dimensionally, it's an eighth. That's called octreeing in gaming. Some of you know about that. Now, what that means is that if you're doing this and you only reduce the energy consumption by half, you're running it at a higher power level than you really should be. It should be a quarter, right? Anyway, Dennard scaling from 1974 dictated that that would happen a lot. It didn't do it every X number of years, but someone noticed that scaling of the transistors, Moore's law, would chop down by half the dimension or half the surface area. The half the surface area thing is actually kind of in this range. If you're using my screen as an example of the chip type. So, I mean, you have to reduce it down this much to drop it by half. You're going to hit a wall where you're no longer reducing it. It's actually getting hotter. It's consuming more energy because at a certain scale, a certain minimum number of atoms are required to do each task, and they produce as much heat and use as much power as something bigger. Getting it smaller wasn't speeding them up much, but it does speed it up. Making them physically smaller can allow more speed because you have less distance for your budget. Okay, now that we've educated ourselves, this is basically first-year solid-state electronics. And no, none of this is accurate. On my honor, everything I'm telling you, you'd need to go look up before you comment to see if I'm wrong, because I'm saying I'm probably wrong, right? Okay, let's go. Going faster requires that you either find completely different chemistries or dopings or materials to work with, selenium tetraoxylininate or some other made-up thing, at least it sounds like it, or you assemble everything in 3 dimensions by stacking it, or you just make multiple processors like you do anyway from a big disk of silicon, and instead of chopping it into smaller chips to make more money, you cut them up in sets of 4 and run them in parallel to try to spread out the heat budget. Or we can have self-assembled crystalline structures that form some magical thing that does processing. There are experiments like that. You can make something called a NAND gate. This is a general purpose chip function. Most of them already do it. Yeah, it's a series of individual electronic parts that are just repeated ad nauseum, and then they're interconnected to behave like a latch for data, something that does logic or math. A latch, if you're not aware of it, can consist of you dropping a voltage on a little square that acts like a capacitor. It acts like a little battery, but it's called a capacitor. Or you can do 4 times the surface area and put it in a set of 4 individual dots. We'll call them fets. I made up that word. It's not like it's field effect transistor. And each of these is configured like this per pair. Each one of them acting like a little push-pull amplifier, so each one of them carries a different value that opposes the other and sends it back flipped to reinforce the other. You know, we would do it like this. And you put your thumb on top for one, and that's how you draw it. And what happens is you force it and compel it to go from this voltage to this one. But it can do it rapidly. And when it does it, it doesn't consume any more power anymore. I mean, virtually none. It only consumes power when you change state because you're coercing it. And you do these pairs with another pair next to it to double check them. Because that's required, because you have to have that. And as the voltage changes at your supposed only, oh, we got plenty of room here, it's a 1-inch budget or 2-inch budget. No. As it transitions, it creates almost a square wave. What that means is it's putting off odd harmonics up into the X-ray range. The packaging on your microchip is opaque, by the way. It doesn't let anything get out. And these can interfere with each other right next to each other. So you hit another upper speed limit and performance limit and heat limit. But we can't do it by making crystal structures that have been, I think, 1 billion experiments now. It's not going to happen anytime soon. Faster access speed, low density, expensive, low load, static gatings can also be done as random access memory for cache. Requires bursts of power only when you have to change its state, and virtually no current, but a little current continually when they're just sitting there, and when you read them a little bit more. but they require 4 spaces on the chip. Dynamic memory, DRAM, is capacitor-based. It's cheaper. You can pack it tighter. 4-to-1. Well, not really, but pretty close. It's 2-to-1. But they require that you refresh them every once in a while to make sure the voltage, you check its voltage state and then top it up. Maintain it either discharged or charged. Now, on a computer, that's like waiting 2 weeks to double check that the mailbox has still got the value in it. Guess which one wears out more often? The expensive shit doesn't. Now, I'm going to bring up something simple here. 2006 is when the heat budget rule of reducing size will reduce power started to fail. Coincidentally, that's between the 2 gigahertz and 4 gigahertz milestones, right? So 3 gigahertz is about the right sweet spot before you start getting diminishing returns. Okay. And you had, let's say, a 4-inch wavelength budget. Okay. Some of you might have noticed the proliferation of low power status computers that used static memory or could go into power down state. You don't see those as much anymore, do you? Coincidentally, that's also when we got really low power, very fast working, fairly good reliability, solid state hard drives. Instead of the ones that lasted decades before they'd forget, we get ones that can go ahead and lose memory if you abuse them and use them too much. Maybe you should just use those as memory cards. No, you should use them as memory storage offline. Go back to using electromechanical hard drives for continuous usage because they're cheap and can be thrown away. Maybe, but let's talk about this. One of the other things consumer electronics noticed is those low-power netbooks that a lot of people laughed at that could run at 3 gigahertz, that worked just fine, they would power cycle to save power, which means they would lower the power usage, not just to save power or to last longer for the battery, but also to control heat because they didn't want to put heat sinks and fans in them. So it would never go to a speed that would age it. You could even force the fan to drop the speed and increase the fan flow to make them last decades. Well, the consumer industry does not want you to do that. And they're still around because I'm using one right now. Because I got in with a soldering iron and turned off its ability to turn off the fan. And I fixed the speed maximum at almost exactly 75% of the maximum at one point. So that it would be just under 3 gigahertz. Well, no, this one only goes up to 2 point something. So I got it to 2 gigahertz and got it stuck there. 6-inch wavelength. No bus contention. No glitches. No bugs. So what's the reason all of this got bogged down? We hit an upper limit because we've hit the lower limit on what we can build. But you don't have a multiprocessor, blah, blah, blah. But your video card's doing all the work, and it doesn't have this upper limit because just like the propagation delays we can accommodate for in a radio transceiver or multiplexer or whatever you want to call it, it's a multiplexer. For doing your cell phone activity, it doesn't have to truly synchronize every bit to where they all arrive at the same time. It can have very high speeds and still be low power based because it can do away with a bunch of all of this compensation shit and just do the job rapidly. That's why video cards are very different than computers. In fact, some computers are just a video card being used and re-implemented as a computer because they work better, because they threw out the idea of making a computer out of them and made them do a special purpose. And now we can exploit some of the functions to do Bitcoin. You know what? You can still buy sub 3 gigahertz, usually 2 point something gigahertz computers out there. You can still force them to run at certain speeds. Anybody remember when Dell Corporation got caught deliberately shutting off heat management and cooling fans to make the computers die more often? And companies like mine just wired the fans on permanently so they wouldn't be able to do that, and the computers still work. Some of you still have them. Hey, that shit grade Dell over there running old Windows XP or maybe running Windows 7 that keeps working. Maybe I should give it a nice loving cleaning and take care of it because we hit the limit actually around 2005 for what we have to work with. Now it's just scaling it up by stacking and packing. Ever notice that Microsoft Corporation and even Google and YouTube are making it to where it's more demanding on your computer than necessary by making more shit go through that isn't really giving you what you want? Consumer grade. Don't you just love it? Thanks for watching. Have a good day. Good luck.